Okay, so modulation encoding techniques.
So whenever we talk about modulation,
in relation to
we
a
can
digital
consider
signal, so
the
what are the
extent
different
to which a
types
signal has been
of
modulated,
modulation which
and
may be
that
applied
extent can be captured in
to
the
the
modulation
signal
index.
in
We
order
can calculate
to
a number in
transmitted
relation
across
to the
the
amount of
communications
modulation
channel.
which has been applied to a
So
signal.
just to recap what modulation is.
Okay, so the
modulation is a process
index,
of facilitating the
it's often
transfer
necessary
of
to define the
information
level of
over
modulation
our
that's applied.
communications
So we want
medium,
to
so
know
over
how
our
modulated signal is, so we can appreciate
carrier
if
waves.
there's under or over modulation.
So we
in
need
order
to extend the range of the
communication within the constraints of
whenever we're transmitting through a medium other than
so
air.
in order to have a standard method of
so if
achieving
you
this,
think about voice,
we use
it
a
can't be
factor
sent very far by
known as the
screaming.
modulation
So we
index.
need some technique for applying
in
it
parallel
to
with the modulation
a
index,
signal,
we can
and
also
allowing that
represent
signal
this
to
as a modulation
transmit
depth.
the information
So the modulation
in a
depth is
more
really just a
efficient
percentage
manner.
representation of the modulation index.
So the process of converting information so that it can be successfully sent through the medium is
undistorted
called
amplitude
modulation.
to
So we're
occur,
converting information in order that it can be supported by the carrier wave.
Okay, so the modulating signal
When we're
voltage
talking
must
about
be less than the carrier
modulation
voltage, so
of digital waves, we're thinking about modulating the amplitude, the phase,
so the modulation
or the
index
frequency.
should
So these are the
therefore
different properties
be
of
a
the
number
sine
which
wave
is
that
between
can be
0
varied
and
in
1,
order
so
to
it
support
represents a modulation
the signal more efficiently.
on a scale between 0 and 1.
So where we have our original signal,
the
we have our carrier wave,
in relation to
and in this example we're applying amplitude modulation.
If the amplitude of the modulating
strength
voltage is higher than the carrier voltage, M will be greater than 1.
Wave.
And when we have an M which is greater than 1,
sine
this
waves are
represents
represented
the distortion
by the expression
of the modulated waveform.
Bx plus
so we've got a modulated signal,
so
but it will be distorted
and C are representative of
the
amplitude,
convey the
the
information
period
which
of
we
the
wish to
wave,
send.
and the phase shift.
So the relationship
so
therefore between the amplitude of the modulating signal
which can
and the
be
amplitude
varied
of the carrier
to
signal is
represent
important to be aware of.
information being communicated through the carrier
Okay, so we
wave.
have a modulating signal and we have our carrier wave. And then we have
so just
our
to give a couple
modulated
of
signal,
examples
which is being carried by our carrier wave. So we want to understand the extent
in this example
to which
here we have an amplitude of 1
the
of our
original
wave,
signal
so our wave is repeating
modulated
periodically
on the carrier
with
wave.
an amplitude of 1. So this graph repeats
so as an
itself
indicator
every
of the
2
level
pi
of
radians.
modulation on
So it repeats itself every 2 pi
modulation
radians.
index is important to know.
And the graph has an
if
amplitude
it's
of
too
1.
low,
So this is our default graph
then it doesn't
against
utilize
which
the
we're going to
carrier
compare
efficiently.
and a series
If
of
it's
other
too
graphs
high,
against.
then the carrier can become
So we have another
overmodulated,
version of
and
the
this
graph.
can
We have
cause
our
distortion
original wave here in
occur, so
red.
interference
And in
the
this graph,
signal which
we
is being
have
communicated.
y equals 2 sin x and y equals 6
So
sin
modulation
x.
indices
So
are
in y equals
described
2
for
sin x,
various
we have
forms
our
of
green
modulation.
wave. So we're modulating our
The
amplitude
amplitude
here.
modulation
And in y
index
equals 6x,
can be defined as
we
a
have
measure
our
of the
blue
extent
wave.
of
So again,
amplitude variation
we're modulating
about an unmodulated carrier
signal according to
so this
varying
describes the
amplitude
extent to
of it.
which the modulated carrier
So whenever we
varies
modulate the
around its
amplitude in
static
this way,
unmodulated level.
you can see how high and low the
so how
graph
modulated
goes.
is the signal
This is the
in order
range of
to
the
convey
wave,
the
okay?
information
So we're
being
modulating that
communicated.
signal according to the amplitude.
So the modulation index, how do we
information.
calculate this modulation index?
Okay, so in this
we have the modulation
of the graph,
amplitude
we're
M,
modulating
and we have the carrier amplitude
signal.
A.
Again, according to amplitude,
and these values
in
are
this
the
example, we
peak
had y equals minus 3 sin x and y equals minus 5 sin
carrier
x.
amplitude and the
Okay, so we have our original wave here in blue, and then you can see the effect of the minus 3
multiplying this modulation index
of the amplitude
by
and
100
5 of the
gives the
amplitude
percentage of the
So
modulation.
we're resulting in different
we have a
series
carrier
of waves
voltage of
based
9
on
volts
variation
and the modulating
of that
signal
amplitude
voltage
value.
is 7.5 volts.
Okay, so whenever we're talking about the phase shift, we're
then we have a
talking about the
modulation
position
factor
of the wave
0.83
time equals to 0.
and the percentage of this modulation, so the modulation depth
we have
is
y equals sin x plus 2.
So there's some
so we
further
have our
examples
original
again at the end
wave
of these
here
series
in
slides.
red. And whenever we're modulating according to the phase, you can see that the new curve in green
so this complementary figure to the modulation index
to the left of the original
is known as the modulation
So we're adapting
and this is
the phase
the modulation
of the
index expressed as a percentage.
whenever we have y
the
equals
modulation
then x
index
minus
therefore of
3,
0.5
the
would be
graph is
expressed
shifted 3
as a
units to
modulation
the
depth
right.
of 50%.
Okay, so again we're working with the phase.
So what does this
in
actually
order
mean?
to modulate
So this means that the
signal.
carrier amplitude varies by 50% above
So
and below
digitization
its
is the
unmodulated
conversion
level.
of the analog
So we
data
have our
into
carrier
digital data,
wave,
and this
once we
digital data
modulate
can
the
then be
information on top
transmitted
of this carrier wave, then
electronically,
the
electrically
wave then
through the
has an
network.
amplitude which varies by 50% above and below
Okay,
its
and
unmodulated
three
level.
digital modulation techniques work on the amplitude,
When the modulation
frequency,
index reaches
and
1,
the
so we
phase
have a depth of
the
100%, then the carrier
So
falls to
to,
0 and rises to twice its
contextualize what that means, we
non-modulated
want to
level.
transmit
Okay,
some
so it
binary
falls to
digits
0
here.
and rises
We
to
convert
twice
that
its
into our
non-modulated
digital
level.
signal. We have our
Okay, so
carrier
we're reaching
wave
here
that we wish to
the
use
outer
to
limits
communicate
of
the
the
information,
carrier wave in
binary
terms
digits,
of its ability to be
and
modulated any further.
to show how this can be achieved
Any
using
increase of
amplitude
the
shift
modulation
keying,
index above
frequency
1,
and phase shift keying. So
okay,
we're varying the
above 1,
amplitude
100%
in this
depth
example.
causes over
So we have a
modulation
different
to
amplitude
occur.
representation
So any
for a
increase
binary
of the
0,
modulation index
and we
above
have
1
another amplitude
causes over
representation for a
modulation.
binary 1. Okay, in this example,
Okay, so the carrier level would
we
try to
have
go
again a
below the
different
0
frequency
point, so it would
for
try to go into level
binary
which the
1.
carrier wave doesn't support.
And we have another
And this has the
frequency
effect
for
of
binary
giving additional
0.
sidebands from
Okay,
the phase
so by
reversals, so
having
that
this
phase modulation
change in the
that extend
frequency,
outwards, and they can extend outwards to infinity.
we are
And this can
conveying
cause
the
interference
binary
in the
information
signal
that's
which is being communicated if it's
And in
not
this
removed.
example, we have a phase shift.
So that's a situation which we want to
are
avoid.
changing from a 1 to a 0. So when we
Okay,
have
so
this phase shift here,
to calculate the modulation
we're
index,
indicating
and
that
this
we're
is
communicating the 1.
a calculation which you
when
should
we
be
have a
familiar
phase
with
shift again,
for your
we're
exam
communicating a
and
binary
also for
0.
your tutorial on Wednesday
Okay,
night.
so by using those variations of the amplitude,
Okay,
the
so we have a
frequency,
modulation
and the phase,
index
it's
which is
possible to
calculated
convey
from
the
the
binary
maximum voltage
information
and the
using a
minimum
carrier
voltage
wave.
of our signal.
So amplitude
So the
shift
modulation
keying,
index is
where we
calculated
vary the amplitude,
using
frequency
this
shift, where
equation.
we shift the
Okay.
frequency, and phase shift keying is where
So if we
the
have
phase of the signal
a
is
signal
shifted.
with a maximum voltage of 10
So
and a
you
minimum
may
voltage of
read
3,
and see about
what is the
amplitude
modulation depth?
modulation
So we
and
use this
amplitude
to
shift
work out the
keying.
modulation
So there's
index, and then
these are
convert
applicable
that
to
to
two
the percentage.
different types of
So we have a modulation index
So the amplitude
of
modulation is in
0.538,
relation to the
and
analog
we convert
signal.
that to the percentage, and we get
Okay, whereas amplitude shift
53.8%
keying
modulation
is
depth.
representative of the digital wave. Okay, so we'll be talking about amplitude shift keying within the context of this series of slides. Okay, so just to summarize again the differences between the different types of modulation techniques. So to look at these in a bit more detail, we have amplitude shift keying. Okay, so we have our carrier wave, we have our information being communicated, and whenever we're applying amplitude shift keying, we're modulating that amplitude of the signal. So one binary digit is represented by the presence of a carrier at a constant amplitude, and the other binary digit is represented by the absence of a carrier. Okay, so we have a 0 voltage where we're conveying a binary 0, for example, whereas when we're conveying a binary 1, then we're representing this in terms of the presence of a constant amplitude. Okay, so we've got two different ways in which we can communicate the binary 1 and the binary 0 based on the structure of the sine wave. Okay, so amplitude shift keying in the context of digital communications is a modulation process where we're using two or more discrete amplitude levels. And these are related to the number of levels which have been adopted by the digital message. So the number of levels that need to be represented in this modulated signal will depend on the levels which are used in the digital message. For a binary message sequence, there are typically two levels, and one of which will be 0. So this can therefore also be referred to as the binary amplitude shift keying. Binary because we're working with two levels. Okay. Okay, so there are sharp discontinuities at the transition points, and these result in the signal having a very wide bandwidth because we're representing the binary ones using the amplitude value, whereas the binary zeros are represented having a zero amplitude. So there's sharp disjoints between transitions from the binary 1 to the binary 0. So advantages of amplitude shift keying: it's simple to implement. The technology used is very cheap and no specialized components are needed. Disadvantages: it's not efficient in terms of power usage, it's not efficient in terms of bandwidth, and it's prone to noise because noise is amplitude based and the amplitude modulating detectors are very sensitive to that, so it can suffer from noise. So frequency shift keying. So a frequency shift keyed message has its frequency shifted. Okay, so the number of waves in a second. So the frequency of the modulated signal is constant for the duration of one signal element, but changes for the next signal element if the data changes. So whenever we're changing between the ones and zeros being transmitted, the frequency of the signal will also change to represent that information. The amplitude and the phase will remain constant, so it's just the frequency which is being adapted. Okay, so there could be more than two frequencies involved, but whenever we're working with a binary, frequency shift keying, we'll only be using two frequencies. Okay, so one for the binary 1 and one frequency for the binary 0. Okay, so this is also thought of as carrying the information using two different carrier waves. So we use the first carrier if the data element is 0, and we use the second carrier if the data element is a 1. Okay, so whenever we are changing from a 1 to a 0 being transmitted, you can see that change in the frequency of the carrier wave. Okay, so that's the way in which the information is being communicated. So two binary digits are represented by two different frequencies near to the carrier frequency. Okay, so you can see here in our sine wave that there's actually two different frequencies which are being used in order to communicate the binary 1 and the binary 0. Okay, so just to represent again, whenever we're communicating a 1, we have one set of frequency being used, and whenever we're communicating a 0, we have a contrasting frequency being used. Okay, so we can think of frequency shift keying as two amplitude shift keyed signals, each with its own carrier frequency. So we can think of as being two signals, each with its own frequency, that's being used to convey this information. Okay, so conceptually, and in fact as well, the transmitter could consist of two oscillators on frequencies F1 and F2, with only one being connected to the output at any one time. So we can have two transmitting frequencies and only one is connected at any one time in order to convey that information. Okay, so the third type of modulation is the phase shift keying. So phase shift keying is a modulation scheme that conveys data by changing the phase of the carrier wave. Okay, so this is the point, the phase refers to the point of the signal at time equals to 0. Okay, so phase shift keying uses a finite number of phases and assigns a unique pattern of binary digits to each phase, and it's through changing that phase that we can communicate the different binary digits being transferred. Okay, so when we're working with the binary, we have our two digits, so we can refer to this as the binary phase shift keying, and we have two different phases to represent binary digits. in each situation. Okay, so we've got two phases in order to represent the different binary digits within each phase. Okay, so the simplest phase shift keying is binary, in which we have only two signal elements, one with a phase of 0 degrees and the other with a phase of 180 degrees. So this binary phase shift keying is simple as amplitude shift keying, and it has one advantage in that it's less susceptible to noise. So whenever we shift the phase, it's not as susceptible as the amplitude shift to noise. So the noise can affect the amplitude easier than it can change the phase of the signal. So the actual signal being communicated is more representative of the information which wants to be sent. Phase shift keying is also considered to be superior to frequency shift keying because we don't need to use two carrier waves. So it's a more efficient use of the communications channel. Okay, so whenever we're communicating our binary 1, whenever we're transitioning then to communicate a binary 0, you can see here that there's a shift in the phase, and it's this shift in the phase that indicates that we're changing the data which is being sent. Okay, and that 0 will be sent until again we see that shift in the phase, and from that point onwards then we're sending the binary 1. Okay, so just to represent that again, whenever we're sending the binary 1 and then we're sending the binary 0, we can see this shift in the phase here. Whenever we're sending the binary 1, again, we can see the shift in the phase. So it's that shift in the phase which signals that we're sending a different data value. Okay, so the digital signal is broken up into individual bits according to time. The phase shift keying uses two opposite signal phases in order to convey that information. So whenever we have that shift in the phase, it's conveying the opposite signal phases. If the phase of the wave doesn't change, then the signal state stays the same. So it's either a 0 or a 1. Okay, so here we're communicating two zeros. You can see that there's no change in the phase of the wave. So the information being communicated is not changing.